Hi, everyone. Thank you so much for joining us today. We'll go ahead and get started in just a couple of minutes. Thank you. Hey everyone, thank you so much for joining us for TrenchBoot and GRUB, a quick introduction as part of the UEFI 2020 Virtual Plug Fest. I'll go ahead and introduce you to our speaker today. So our presenter today is Daniel Kipper, who's a software engineer at Oracle. And I'll go ahead and pass it off to Daniel.
Oh, thank you for the introduction. I would like to, I prepared this presentation together with Daniel Smith from Apertus Solution. As it was said, I work for Oracle. Currently, I'm also GRUB maintainer and work on TrenchBoot project. Today, I would like to introduce you into the TrenchBoot and the GRUB. In general, at the beginning, I would like to tell you some things about the TrenchBoot, what it is. Also, I will compare how the TrenchBoot works and UEFI Secure Boot works, and I will compare these two things. And finally, I will tell something about the GRUB, or I will tell why we decided to choose the GRUB as a bootloader for TrenchBoot project, and also discuss the current state and challenges in the GRUB development. And at the end, I'm happy to reply for your questions. So let's start from the TrenchBoot. In general, the TrenchBoot is cross-community integration project focused on launch integrity. It is worth mentioning that there is no one thing which is called TrenchBoot. The TrenchBoot project consists of three main parts. One is the Linux kernel, another one is the bootloader, in this case GRUB, and third part is init.rd, which is based on root project. The name is playoff of dealing with muddy mess of trying to find a way to unify boot integrity. The aim is to develop a common unified approach to build trust into the platform for launch integrity. So we will, as I said earlier, we would like to integrate various open source projects to provide dynamic launch solution to various open source projects and operating systems. For example, Zen, KVM, Linux, BSDs, but also we consider to provide support for dynamic launch for proprietary kernels. Oops, I think it's too far. Okay. So the idea of TrenchBoot originated in 2013. When some folks were playing with OpenXT and tried to launch Zen using tboot. During this work, they learned that tboot has many limitations, And they realized that maybe it makes sense to think about a new project which will provide dynamic launch support and much more. As I said, during this work, the folks discovered many deficiencies in TrenchBoot. So, for example, there are some difficulties with access to the event log. There are some conflicts with UEFI, with access to the UEFI boot services. TrenchBoot allows you only to measure multi-boot modules that were loaded into the memory by the bootloader. And TrenchBoot supports only one attestation action, which is determined by the PCR manifest. And last but not least, TrenchBoot supports only Intel TXT. So there is no support for AMD Secure Startup, and also it means there is no support for other architectures and platforms. So, because launch integrity is the foundation for the platform security, we stated that dynamic launch deserves much more attention from open source project, and it should be implemented properly. Additionally, in the past, dynamic launch was underutilized. Currently, if you use dynamic launch, you use it just only at boot. But in fact, it is possible to use dynamic launch many times between power on and power off. So each dynamic launch is an opportunity to establish the current integrity of the platform. So TrenchBoot for Linux provides different strategies to build trust in the platform. The first case is a well-known case which is provided by TrenchBoot 2. It is called first launch. And in this case, the trust is established and rooted in the hardware during platform boot. The second case, called runtime launch, establishes hardware-rooted integrity during platform runtime. The second case is very interesting because it can be used to do many interesting things. For example, it can be used to do secure launch for kernel upgrade. It can be used to verify integrity before executing a privileged operation. It also can be used to establish platform state after sleep or hibernate. The runtime launch also can be used to review platform state before rebooted shutdown and check integrity before persisting machine state to the disk. So, who contributes to the TrenchBoot project? The TrenchBoot project was initiated by Daniel Smith from Operative Solution. He invited Oracle and FreeMDEP to the cooperation on TrenchBoot project. Later, C6 joined, and recently Intel also decided to help us with the project. In general, Daniel Smith from Operative Solution coordinates all efforts with regard to TrenchBoot. Oracle focuses on Intel implementation in the GRUB, the bootloader, and the Linux kernel. Also, Oracle added a few needed features to URoot project, which is a base for initRD. FreeMDEP together with Citrix focuses on AMD development. So let's have a look at the terminology which is used in the dynamic launch area. Unfortunately, this terminology is very confusing because we have three sets of terminologies which are used in this area. The first one, which is common and vendor independent, was provided and it is introduced by TCG in dynamic launch specification, and this is generic one. But there are also two terminologies which were introduced by vendors. One is introduced by Intel in Intel TXT specification, and the other one is introduced by AMD. So as you can see, sometimes the same thing is named in three ways. For example, we have a very good example, platform-dependent event that triggers the dynamic launch. In TCG's specification, it is called dynamic launch event. In Intel TXT doc, it is called getSecCenter, but AMD specification is called SKInit. There are also some terms which are only used in TCG specification. Good example is DRTM configuration environment preamble. And I would like to discuss two more terms which we'll be using in this presentation. In general, we'll be using in this presentation TCG terminology, so the common one. But sometimes we'll be referring to some specifics of Intel or TXT. Then we'll be using their naming, dynamic. So let's have a look at two things. One is called DRTM configuration environment. Usually it is a piece of software, small piece of software which has limited size, which is executed after a dynamic launch event. This piece of software is responsible for checking platform configuration and its initialization. Also, it is responsible for taking measurements of various components during dynamic launch initialization. On Intel TXT, it is called Authenticated Code Module, ACM, and on AMD, it is called Secure Loader. Another piece of software which doesn't have any size limitations is called Dynamic Launched Measured Environment. This is piece of software which runs in very controlled environment which was initialized by DCE, DRTM configuration environment. It allows you to do it tells you to do very different things in very controlled environment. So it is very important. I will discuss this later, and I think that it will be much easier to understand what it does exactly. So let's move on and compare how UEFI Secure Boot and dynamic launch works. So let's have a look at UEFI Secure Boot first. So machine boots or is initialized by reset vector, then UEFI firmware is loaded from the flash memory into the RAM, and then execution starts. The CRTM, core root of trust for measurement, is not measured until during the PEI. So it means that SEC and PEI code has to be trusted. But the CRTM is of SEC and PEI. So this means that we have a loop here, and it is self-referential. So the CRTM relies on integrity of boot flash, and it relies also on TPM to protect measurement. The DXC phase enforces UEFI Secure Boot verification. So we have, in case of UEFI Secure Boot, we have three roots of trust. First one is root of trust for storage, which consists of flash and the TPM. Root for measurement, which consists of SEC and PEI phase, and root for verification, which consists of three parts: SEC, PEI, and DXC. Let's compare this to dynamic launch. So dynamic launch is initialized by DCE preamble. DCE preamble can be a bootloader or an executing OS. So when when dynamic launch is initialized, the CRTM is taken by the CPU. It only relies on the TPM to protect measurements. On the Intel platform, we have additional authentication protocol between DCE and CPU. It is just based on signatures. The CPU checks the DCE signature. The CPU checks the DCE signature before executing it. So DCE takes measurements. CPU takes measurements of DCE, and after that, when DCE is executed, it takes measurements of the DLME. So this is much simpler than UEFI secure boot case because it relies only on the hardware. So dynamic launch provides very controlled and protected startup because it relies on many hardware features. First of all, the CPU obtains locality number 4 on the TPM and clears all DRTM PCRs. All CPU interrupts are disabled, and the CPU protects the DCE from DMA accesses. On Intel platforms, the CPU uses something which is called cache as RAM. On AMD, it depends on device exclusion vector. The DCE is measured by the CPU, as I mentioned earlier, and the results of these measurements are stored in PCR 17. On the Intel platform, ACM is also authenticated using signatures. The AMD platform is a bit different because the AMD doesn't provide DCE module. The AMD requires that a platform owner has provided own secure loader. So it also means that AMD is not able to do additional verification of this module because it cannot be simply signed by AMD. And DCE ensures that DLME is DMA protected, measures it, and then executes it. The result is very high integrity assertion of DLME. So as you can see, the boot firmware is completely removed from TCB, unfortunately with exception of SMA handler. This is good, but there are some problems with this approach on UEFI platforms. This means that if you run in dynamic launch environment, you shouldn't call into UEFI because it doesn't belong it is not part of trust, let's say. So, for example, you are able, but you shouldn't call UEFI runtime services to, for example, change the variables or change the boot order or something like that, because then you are starting executing the code which was not measured and is not part of your trust. So let's have a look how the boot process in first launch looks like. So at the beginning, the platform is initialized by the firmware. For example, firmware and then UEFI, and then control is passed to the bootloader. In our case, it is the GRUB, and the GRUB may take some measurements and put them into the TPM. This is not required, but sometimes can be useful. So then you have a static root of trust. And GRUB checks the platform configuration and then passes the control to the DCE. On Intel, it is called ACM, as I said earlier. On AMD, it is secure loader. Secure loader and ACM does further platform checks and also take measurements of the DLME and put the results of these measurements into dynamic PCRs. And if everything is okay, then the control is passed to DLME. DLME in TrenchBoot consists of two things. One is the Linux kernel, and another one is initrd. Initrd is built on top of your root project. So the control is passed from DCE to the Linux kernel first, to be precise, to the early part of Linux kernel. And this early part of Linux kernel does final configuration platform checks, and it also takes some measurements of arguments which were passed from the bootloader, in our case the GRUB, to the DLME. For example, it takes measurements of command line which were passed to the DLME. And after that, the control is passed to the Linux kernel proper. Linux kernel proper does final platform configuration. It starts up all APs, etc., and then further kernel initialization proceeds as usual. And after that, the control is passed to initrd. And initrd provides us a lot of flexibility, because you can use almost anything in initrd. You are able to just any user space process which you can imagine. So you can do different actions in very protected environment. In general, we extended root with a few features which allows us to do, first of all, do various measurements. For example, you can take measurements of file systems, block devices, but you're also able to get measurements of various system components. For example, you can take measurements of CPU IDs. So this is very flexible solution. We are also able to provide some attestation functionality. Currently, it is on our to-do list, but we are also going to provide this functionality. And if all actions which were described in policy file for initrd were executed correctly, then control can be passed to the target OS. We use to pass the control to the target OS the kexec functionality. We call it kexec launcher. And the kexec just on Intel platform. On the Intel platform, it closes access to the dynamic PCRs. It also seals these PCRs, and then shut down DLME and starts target OS as usual. So as you can see, this boot process is very flexible and can be very nicely configured. So this means that it gives you a lot of possibilities to do many things in dynamic launch. So let's have a look at the GRUB history, and also explain why we decided to use this project in the TrenchBoot, and later I will tell you what's happening in the project right now. So the GRUB project was initiated by Eric in 1995. He was working on starting GNU hard at the University of Utah on their machines, and the outcome of this work was a multi-boot specification. Eric tried to implement this specification in FreeBSD bootloader, but he quickly realized that it was easier to write on bootloader from scratch. So this way, GRUB was born. In 1999, GRUB was adopted as an official GNU package. Over the next few years, GRUB gained a lot of very interesting features. But during this work, it became clear that design is not keeping up with the extension being made. So around 2002, new project was started. The goal was to rewrite the core of GRUB to make it more flexible and allow you to provide more features in a much easier way. This project was later renamed to GRUB2, and the original version of the GRUB was renamed to the GRUB Legacy. GRUB Legacy was released. The last version of GRUB Legacy was released in 2005. Major Linux distributions migrated to GRUB2 between 2007 and 2009. Why we decided to use the bootloader? First of all, this is the most common bootloader in current deployments. So this is one very good feature for us. But I think the much more important is that it is the most feature-rich bootloader currently in the wild. First of all, it supports at least 24 variants of architectures, including ARM, x86, Itanium, MIPS, Power, RISC-V, Spark, and platforms like UEFI. It also supports many file systems, including file systems with encryption like LUKS. It has many security and crypto features embedded, including UEFI Secure Boot via Shimlock protocol and TPM support. The GRUB can start directly from ROM, and to do that you have to integrate the GRUB with CorDeboot project. The GRUB also supports many different boot protocols, including TFTP and HTTP. The GRUB also has embedded minimal shell capabilities, which allow scripting, and many more. To give you an idea how the GRUB is flexible, I would like to tell you that I heard that some people use the GRUB to attest the firmware, and more interestingly, I heard that some folks also provide BIOS graphical menu using GRUB, and this way you are able to configure your BIOS using graphical or text menu. So this is very interesting, and I think that it shows that the GRUB is a very flexible project. So let's have a look how GRUB and UEFI works. So the GRUB works on all architectures which are capable of running UEFI, and most UEFI features are currently supported by the GRUB. I mean features which are needed to boot the operating system. We are not going to implement features which are needed to start operating system or something like that. So we don't care much, for example, about runtime services. So the GRUB also supports UEFI Secure Boot via Shim. It has to be done in that way due to various things. First of all, the Microsoft didn't want to sign the GRUB due to legal issues. The problem is that the GRUB is licensed under GPL v3, and it means if Microsoft signed the GRUB, it would mean they have to be obliged to release the signing keys to the public, and this is what they do not want to do. So this is the first thing which they do not want to do. Another is that on some architectures we do not use UEFI calls to load and execute kernels. So we are not simply hook up into UEFI's secure boot infrastructure directly. So this was another problem. Another feature which is very useful and used by different companies currently is support for UEFI for measurement using UEFI TPM calls. So as you saw during the presentation, you are able to do measurements of various files which are loaded by the GRUB. Also, you are able to measure the command line and other things. In general, each file which is loaded from disk is measured by the GRUB. So all modules, all kernels, all other files are measured by the GRUB. So everything is measured, and this is reflected in relevant PCRs. The GRUB can load many different operating systems, even operating systems which even sometimes do not support the UEFI at all. Quite interesting feature is that the GRUB presents the unified interface to the user, regardless of the architecture and the firmware. So this is if, for example, a user was used to one platform, for example, x86, he or her is able to move to ARM, and then he will see the same interface. So this is very convenient. As I said earlier, the GRUB also supports basic scripting, and this is very useful for automation. Also, it is possible to integrate with other languages. I heard about some integrations with Python. There is no support for this integration in the upstream yet, but we are also discussing to introduce this thing into the GRUB. And last but not least, currently the GRUB community is pretty active. So more and more features are posted on the GRUB devel, and we are discussing support for different new interesting features. So what are the current challenges in the GRUB project? First of all, as I said earlier, we have some problems with UEFI Linux boot protocol. Unfortunately, it is different in some cases. On x86, this boot protocol doesn't use UEFI calls to load and execute the kernel. This is due to historical reasons. The Linux kernel was booted in special way on x86 platforms, and when UEFI appeared, then this protocol was extended with additional things which were needed to properly start UEFI, Linux kernel in the UEFI environment, and also pass some information from the UEFI to the Linux kernel. So recently, Art, who is maintainer of Linux UEFI infrastructure, decided to unify these all protocols on all architectures and put this implementation into the Linux kernel. So our goal for the GRUB project for the following months is introduce this unified UEFI Linux boot protocol into the GRUB, and this way we'll be able to boot the Linux on each platform in the same way using UEFI calls, which means that also allows you to use secure boots directly without shimlock or something, like that. Of course, it doesn't mean that GRUB will be signed by Microsoft due to these legal issues, but if you, for example, need to use the GRUB internally on your UEFI secure enabled platform, then you can do that, just sign the GRUB and execute it on your platform, and everything should work. And further, we would like to add this unified UEFI boot protocol to other OSs. We discussed this thing recently in the Zen community. So I think this will be probably implemented, but a bit later. But our goal is to unify UEFI boot path in the GRUB. So these are two challenges which we are going to solve. Another is we have some long-standing network boot problems on UEFI platforms. This is due to issues with SNMP driver. As you may know, SNMP driver can be used only by one application in the UEFI. So if earlier something in the UEFI was using SNMP driver, then GRUB doesn't receive packets from the network and just simply is not able to put the operating system due to lack of access to the network. We are thinking about implementing MNP driver or something like that to solve that problem. This is under discussion. I hope probably we will backport some solution from distributions which have this problem solved. And last but not least, currently the project struggles with shortage of reviewers from firmware and OSS sides. The problem is that, as I said earlier, the GRUB community is getting more and more active. So there are more and more patches posted on GRUB Devel, and also more and more questions are asked on the GRUB Devel, and unfortunately we are not able to reply to all of them as quickly as we want to. So this is our problem, which we are trying to solve. We are trying to encourage people who have expertise in different areas of booting operating system or firmware to join the project and to review the patches. Even a review for 1 or 2 patches helps us a lot, because sometimes we don't have expertise in a given OS or in a given platform or firmware. So we are if you are able to join the project, it would be perfect help us. Situation is slowly improving, but we need more and more eyes looking at the code or replying for the questions which are appearing on GRUB Devel. We are also working on some improvements to our development infrastructure. We are going to introduce some automation to the review process. Also, we would like to introduce some automation for testing, etc., etc. Probably we also integrate some things with such well-known sites like GitLab or GitHub. So this is more or less, I think, about TrenchBoot and GRUB, and I'm happy to reply for questions. The first question which I got is, where may I find more details about TrenchBoot project? I prepared a slide with references to basic sites which describe First of all, the DRTM, which is used in the TrenchBoot project. And these first two links describe, one is the specification and one is overview. So it is worth starting looking at, if you want to get familiar with the DRTM, I think it's better start with looking at specification overview. The TrenchBoot project is available on GitHub. The GitHub site contains the code, specific, also documentation. The project is on active development. The patches were sent recently to the Linux kernel mailing list and also to the GRUB devel. They are under discussion. Also, as I said earlier, the URUT project merged our code, which is needed to run the TrenchBoot and use its features. And there are also some GRUB sites. The first link on GNU site is a main GRUB website, and also it is worth looking at GRUB devel mailing list. This link contains links to the archive of GRUB devel, and also you are able to sign up to the mailing list. The next question is it possible to run TrenchBoot on UEFI platforms? Yes, the goal for TrenchBoot is to make it run on each, let's say, piece of hardware, regardless of firmware, and in further future probably regardless of the architecture. For example, FreeNDEP works on AMD implementation, which doesn't depend on UEFI, so you are able to do that. And next question: are there any potential difficulties with running TrenchBoot on UEFI platforms? Yes, there are difficulties with running TrenchBoot on UEFI platforms. The first problem is that if you want to start a dynamic launch, you should shut down boot services before exiting from the bootloader. So it means that, for example, the Linux kernel, which is used in the LME, is not able to run its initialization using boot services. So this complicates the situation because we have to duplicate the functionality which is in kernel and which uses the boot services to get information about the platform configuration of, for example, the memory map. We have to duplicate this functionality in the bootloader. Fortunately, some parts of this thing exist in the bootloader, so this is not very complicated at this point. But of course, this is a code duplication which is not a very nice thing. We discussed this on the Linux kernel list, but unfortunately we haven't found up until now the better solution. Another thing which I mentioned also during my presentation is that you shouldn't call from your DLME environment runtime services, because runtime services are not part of trusted environment. So it means you are going out from trusted code to untrusted code. So this is the problem, because, for example, we are not able to change the boot order of the machine. We are not able to send updates to the firmware, and you are not able also to change the contents of variables. As I said, it's possible, but you shouldn't do that. We're currently discussing how to solve that problem, but it is difficult. Probably this will be discussed in this year in various conferences. So I think that we will find solution for this issue. So I think that's it about questions.
Great.
I think that I'm finished.
Well, thank you so much, Daniel, and thank you everybody for joining us today. As just a note for the attendees, these slides will be available on the UEFI Forum website, and a recording of this webinar will be available on the UEFI Forum Bright Talk channel, as well as on YouTube. So thank you all for joining us.
Thank you. Bye.